screen. And there we go. All right. So last time on Wednesday, we were discussing the chapter on equilibrium. And we were using this reaction as our first example of a reaction that goes to equilibrium. And we had noted that everything is heading towards equilibrium in the universe. And when we get to thermodynamics, we'll take a look at the energy basis for why things proceed spontaneously towards equilibrium. But anyway, you can imagine this reaction of N2O4 goes to NO2. In the beginning, maybe we start out with all reactant, then we produce some products, but there becomes a point where the rate of the reaction forward equals the rate reverse. And that's when we call that point in a reaction lifetime equilibrium. And we say that that reaction has reached equilibrium. And there's a lot of ramifications from that idea. And so we took a look at some of the things that happen. We said, okay, we can have a reaction A goes to B, its rate could be first order. The back reaction B goes to A, its rate is also first order. At equilibrium, those two quantities should equal. So when we write them equal, when we group the concentrations on one side, the constants on the other, we see that the ratio of concentrations should equal a constant. So we introduced this idea of ratio of concentrations equaling a constant at equilibrium because the concentrations don't change. So we took a look at this, this graph last time, and we said, okay, this is the kinetic region here where we have changes of concentration, but then we get to a point in time where they stop changing. And in this picture, we noted that at equilibrium, the concentration of the reactant is higher than the concentration of the product. But that's not always the case. But it alludes to the idea of one of the main purposes of studying equilibrium. Because if you're running a reaction in the lab or in an industrial setting or whatever, I think one of the purposes of running the reaction is to maximize the number of products. And so if you get to an equilibrium where you have more reactants than products, then that's probably not an advantageous equilibrium. So if we study equilibrium and we study the factors that govern equilibrium, maybe we can help this reaction change to where we have more product at equilibrium and less reactant. But anyway, that's coming up maybe in today's discussion. And then we have this plot over here where we look at the rates of the forward and the reverse reaction as a function of time. We see that the rate backwards of the reverse reaction 0 initially because there's no B. But then there becomes that point in time where there's an equilibrium and the rate forward equals the rate reverse. So that time corresponds to the equilibrium time in the other plot. All righty, so if there's any questions on anything, please.
So just to clarify, so they're going to a point where they just stop changing concentration, but they don't necessarily have the same concentration.
Yes, and on top of that, not only do they not have the same concentration, but the reaction is said to be dynamic. And that means that the reactions are still taking place. For example, if we look back here, we can look back or forward, it doesn't matter. Let's go forward. If this reaction reaches equilibrium, we represent that by the double arrow or something that looks like this sometimes, or one of those versions of that double arrow. That means that that reaction reached equilibrium. And for every 3 hydrogens that react with 1 nitrogen, at that same time, there's 2 ammonias that back react. So the reaction is dynamic. It's still taking place. It's just that it's taking place at the same rate forward as reverse. So I hope that answered your question.
Yeah, that's good. Thank you.
Okay, thanks, Stephanie. Any other questions? Like I said, just interrupt me at any time. It doesn't even have to be about the stuff that we're talking about. It could be something that pops up in your head about lab or something, and you say, "Oh, excuse me, it doesn't have anything to do with what you're talking about now, but I just thought of it, and I know something." So don't be shy. All right. So moving right along then. Last time we talked about this Born-Haber process for making ammonia, and we wanted to think about this reaction in terms of equilibrium. So we plotted out some changes of concentration versus time for 2 extreme scenarios. One scenario up here is where we started with just reactants and then came to equilibrium here. And scenario 2 was where we just started with products, just product, no reactants, and then came to equilibrium. And we mentioned that these concentrations may not be the same in each of those cases, but what this idea is saying and what the math is showing is that the concentrations might not be the same at equilibrium from one to the other case, but what is the same is the ratio of the concentrations. That's always a constant, just like 6/2 equals 9/3. They both equal 3. And so you can think of an infinite number of possibilities in between that case 1 and 2, where you have some mixture of reactants and products and let them go to equilibrium. Just let them go, and they're going to go to equilibrium naturally. And when that equilibrium's when the equilibrium is reached for any of those cases, what's going to be constant is the ratio of the concentrations.
Oh,
So that
Professor, that's saying basically over here to the right, it says start with no matter however you start the H2 into it NH3, however you start splits, it's going to end the same way when it splits and it comes into its products, right? When it comes into equilibrium, that's basically how it's going to end either way, how the same ratio.
correct.
Okay.
That's right. It's the ratio that's going to be the same from one case to the next. And it doesn't matter what you start with, as long as you start with some of all the reactants or some of all the products. Now, let me explain what I just said. Now, if I start with, for this case, let me see if I can go. We talked about a whole bunch of stuff last time. I don't want to skip that far ahead. All right, let me go back to this case. Now, if we started out with 0 H2 and 0 N2, but we had some ammonia, then we see that for this to reach equilibrium, it has to make some H2 and N2, even if it's a small amount, and that the equilibrium constant is large and this equilibrium lies to the right. It has to go to the left just a little bit. And the second law of thermodynamics tells us that, and we'll get to it when we look at thermochemistry. Now, if I start with, say, just some N2, I can't expect this reaction to come to equilibrium unless I have some H2 in here too. Because I can't use just N2 and make NH3 with it, right? There's no H in there. So I can't do that. So you have to have some of all that's on one side or the other. I could have other products here, you know. So if I had other products and I wanted to shift to the left, then I would need some of this and some of this. So that's kind of subtle now, but hopefully we'll get to some more examples of that point later. All right.
That makes sense. Thank you, Professor. Thank you.
Yeah, sure. The point so far, though, is what you said, which is it's the ratio of the concentrations. It could be product over the concentration of the product over the reactant, or the reactant over the product. That ratio is going to give us a constant, no matter what the initial conditions are, as long as we have initial conditions that can produce an active reaction one way or the other, towards the products or towards the reactants. All right. So then we went along and we introduced this special ratio of concentrations using what's called the law of mass action. And the law of mass action says, okay, say I have some generic reaction with stoichiometric coefficients in the small letters. The capitals represent the reactants and the products. So a special way to form that ratio is using the law of mass action, and that's used to define what we call the equilibrium constant K. It's a constant, and it's formed by taking the concentrations in units of molarity of the products to their stoichiometric coefficients and divide that by the concentrations of the reactants to their stoichiometric coefficients. When you do that special ratio, that's defining the equilibrium constant using the law of mass action. So in other words, as soon as you write down any old reaction, it's connected to an equilibrium constant. It's defined by that. So as soon as I write it down, I'm defining N2O4 as a reactant and NO2 as a product. So I know how to write my equilibrium constant. And this one was given because someone went to the lab. They allowed this reaction to take place. After some time, they noticed the concentrations didn't change. They calculated the concentrations experimentally. They plugged in the numbers, and they found at this temperature, that's what the ratio equals. So now anybody in all over the world can do the same reaction at the same temperature, and they get the same answer. Okay, so that's our introduction to equilibrium constants. Let's move this out. And we went on to say, well, there's other equilibrium constants, for example, Kp, where you use the same definition, concentration of products to the stoichiometric coefficients over the reactants to theirs. But for Kp, you use units of atmospheres, and its partial pressures of the products, P and Q, to their stoichiometric coefficients over the partial pressure of A and B to their stoichiometric coefficients, A and B, all in units of ATM, whereas Kc was formed in units of molarity, even though these equilibrium constants, Kp and Kc, are both unitless. So there's no units associated with the equilibrium constants themselves, just on how they're formed. And there's a relationship between Kp and Kc using the ideal gas law, which we looked at. And so there's a factor of RT to the delta N that equates them, where R is that ideal gas law constant, liter atmospheres per mole Kelvin. And T is the temperature in Kelvin. And delta N is the number of moles of gas that are changed from reactants to products. So we looked at an example of how to calculate delta N. Here, it's always final minus initial. So I have 2 moles of gas initially and 4 moles of gas. I'm sorry, the other way around. I have 2 moles of gas in the product and 4 moles initially in the reactants. So it's final minus initial. I get a -2 for my delta N. So I know RT has to go to the -2 to calculate Kp from Kc. So we looked at that, that relationship, and we moved on from there. We wanted to talk about some of the terminology that's often used when studying the concept of equilibrium. This idea of the magnitude of K gives you insight as to the complexion of the mixture at equilibrium that you might expect for any reaction. So one thing you can study about a reaction is its equilibrium constant. Once you see the magnitude of that equilibrium constant, and we mentioned what magnitude meant, it's just the value of the number, irregardless of the sign. Well, having mentioned that, equilibrium constants are always positive because you can't have a negative amount of something. So it's all magnitude. It's all the value. But anyway, oftentimes scientists will talk about the magnitude. That's what they mean. They mean the number value. So the lingo goes that the larger K is, you would expect more products at equilibrium relative to reactants. And so we say that that equilibrium for that reaction lies to the right, towards products. Smaller K is just the reverse. That equilibrium indicates we have a situation where you'd expect more reactants than products. So we tossed that idea around. We took a look at a little picture of what's that meant to have a large equilibrium constant. For example, 1,000,000, 10 to the 6, versus something that's really tiny, for example, 10 to the -6, fractional. Notice neither one is negative. This is just a positive point. 1, 2, 3, 4, 5, 1. Yeah, right? So this value, 10 to the -6, equals 0.000001, or 1/1,000,000th. It's not negative. It's just less than 1. And so that's what it's telling here. When you have something that's very small for an equilibrium constant, expect mostly reactants. All right. So then we went on to taking a look at that reaction again, N2O4 in equilibrium with 2NO2. When I write that down, I define the reactants and products, and using the law of mass action, I can form the equilibrium constant. Kc, when these are in units of molarity here, even though the value is unitless. But this also implies that if I had written this in reverse to what was up here, then I would have defined a different equilibrium constant. But this equilibrium constant is related to this, and it's related in an inverse way. So if I called this Kc1 and this Kc2, then Kc1 is inversely proportional to Kc2. And in fact, it equals the inverse. It's not only proportional. And you can see that through the definition. This Kc is defined with N2O4 on the top, whereas this Kc is defined with N2O4 on the bottom. And so I would just take the inverse of that and find my other K. So one of the things that this is good for is now that we understand this, we've just cut all the tabulated equilibrium constant values in your textbook or online in half. So there's no need to tabulate both of these, one or the other, and you can figure out which one you need after. All right, so this is all just a review, just some of the stuff that we were thinking about last Wednesday. So moving right along, we then mentioned that, well, there's going to be some things in the equilibrium constant that are also constant themselves during a chemical reaction. For example, any solid is going to have a constant concentration. And so we proved that last time by saying the concentration of a solid is its density divided by the molar mass. So this is grams per mole. And the density of a solid doesn't change during a chemical reaction, and neither does its molar mass or its molecular weight. So if a reaction takes place with a solid in the bottom of a beaker, yeah, okay, so we lose some of the solid and maybe it dissolves, but its concentration doesn't change. So what is done in science is to incorporate any constants in concentration into the equilibrium constant and post that online or in your textbook. So now when I see a reaction that involves solids and I want to form the equilibrium constant for it and associate it to something that I find in your textbook, I'm going to have to realize that the concentrations of any of the solids are not shown explicitly in the definition of the equilibrium constant using the law of mass action, because those constants are already taken into the equilibrium constant itself. So the equilibrium constant for this reaction, Kc, is just the concentration of CO2. Just like it's depicted in this plate. Here's the old equilibrium constant, concentration of the products over the reactants, but a product and a reactant are both solids. This is constant. So it's put in here. And this is what you find in the textbooks or online reference values. I think I mentioned that this is also true for aqueous types of reactions. So if you have a solvent that's in the majority, then during a reaction, it might be consumed a little bit, or it might be produced a little bit, the solvent. But in all intent and purposes, its concentration is pretty much the same. So if it was 1 molar and a little bit got used up, it would be 0.999999999, say, and that's pretty much 1. So that's often incorporated in there. The one solvent that we use mostly in Chem 201, we mentioned last time, is water. And we looked, I think, at a few cases of this where something like HCl reacted, whoops, and formed some aqueous Cl minus. Sorry about the handwriting. I'm free air in it. So K for this would be concentration of H3O plus times Cl minus over HCl. And so water is the solvent. We know that because these are aqueous solutions and it's in the majority. So it's not represented.
I have a question. I don't know if it's kind of dumb, but for when it says constant times CO2, what is that constant? It's not Kc, right?
No, it's this Kc. It's the constant that we use
Oh, okay.
on the definition of the law of mass action. So what I did was I took this constant, divided it by both sides, and so this Kc here is divided by the constant this. So this here is this here.
Okay, thank you.
Uh-huh. And so we divide that out. We call that the new constant that has incorporated the solids in it. And now we're only left with that. Okay. Thanks for the question. And then last time we said, all right, let's take a look at some equilibrium problems that you might see. This one probably is too easy to have by itself. It'll be embedded in the other types. But anyway, the type that I call type A is when in the problem, they give you all the equilibrium concentrations. So all you have to do is apply the law of mass action in the definition of the equilibrium constant and plug in the values that they give you, making sure that the stoichiometric coefficients are represented because that's how it's defined. And you calculate your equilibrium constant. And then we went on and said, well, there's a couple other types that you're going to need to know how to solve, type B and type C equilibrium problems. And we also mentioned last time that in Chem 200, in order to figure out what concentrations were left at the end of a reaction, you use limiting reagent techniques. And so we said, well, geez, limiting reagent techniques, that's only good for a reaction that goes to completion. And most reactions don't. So we have to use equilibrium techniques to find what the concentrations are when the reaction sort of gets to the end of its life. In other words, it reaches equilibrium. Completion reactions, you run out of something like combustion. Then you can figure out what's left of the other reactant the limiting reagent's gone, and you can see how much is produced based off of that limiting reagent. Here, we don't have a limiting reagent in equilibrium. So a way to figure out what you have at equilibrium is going to be the type C problem that we're going to look at in a second. But before we even get to that, we introduce what's called the ICE table. And the ICE table allows you to represent information given in a problem in an organized fashion, so you can relate that information to the equilibrium constant and equilibrium concentrations. So we want to use the ICE table because later on, when we study acid-base equilibrium and other equilibriums, we're going to introduce other factors that are going to be related to the concentrations and the equilibrium constants. And it's going to get confusing on how they relate. And the best way to do to organize your data is an ICE table. For example, we mentioned other things that we're going to want to look at are the pH of these solutions and how that relates to the concentrations and the equilibrium constant. Also the percent ionization, the solubility, and so forth. So this slide talks about the ICE table a little bit, but we went right to an example to show the application of what that slide was talking about. So we looked at this problem that places some NaCl in some water, and it comes to equilibrium. So since they didn't say anything about the products, we assume that there's zero initially. So we write this ICE table to organize the data that's given to us in the problem. ICE, the change row, and the equilibrium row. Now in these problems, when we have to calculate K, what they do is they give us the initial conditions, or we can figure them out by reading between the lines and figuring out what they didn't give us would be 0. And then they give us 1 at equilibrium. And it doesn't matter which one they give us at equilibrium. It could be any of these guys. All we need is 1. Once we have 1, we can use the change column along with the stoichiometric coefficients of the balanced chemical equation to figure out what the changes must have been for the others. So that's the important part of the change column, using those stoichiometric coefficients. All right, so I know that at equilibrium, NO is 0.66 molar. So I know its change must be 0.66. And I know that that equals 2 times some value, where X would be the value of the change associated with any of the reactants or products with a stoichiometric coefficient of 1, which in this case is this guy. Sometimes none of the things in your balanced chemical equation have a stoichiometric coefficient of 1, but it doesn't matter. That stoichiometric coefficient is used along with some algebraic parameter X, or whatever you want to call that. It doesn't have to be X, it could be Y. You could name it, I don't know, little guy or whatever. But in math, we usually use X. So if this is a 2 here and this is a 2 here, then this value has to be the same. And this value over here, since it's a 1, has to be half of that. All right. And so we looked at that and we said, okay, well, once we have the change columns, I can add up, the change row, I can add up these guys. That's already added, and find out what I have at equilibrium, but I have to know the sign for the change column. In order to do that, I have to know which way this reaction shifts towards equilibrium given these initial conditions. So I look at the initial conditions. I see, well, I start out with some reactant and I have no products. So I ask myself, which way does this reaction have to shift to reach equilibrium? Well, this is what I call sometimes a no-brainer. It can't shift to the left because you don't have any here. You can't take nothing and make something from it. So it has to shift to the right to reach equilibrium. Therefore, the negative signs have to go under the reactant and the positive signs have to go under the product because it's shifting to the right to reach equilibrium. So now you can add these all up like we did last time. And you can find your equilibrium conditions. And then once you have your equilibrium conditions, it becomes a type A problem. You just form the equilibrium constant using the law of mass action and the stoichiometric coefficients. And then you put in those values and you square them when you have to, crunch it on your calculator, and find the equilibrium constant. And so that's all the stuff I think we talked about last time. And we left off there. So I'm going to pause for a second to see if anyone has a question. And I'm going to take a drink of tea.
So Professor, for that problem, so say it wasn't 2 moles of NaCl, it was like 4, you would multiply 4 times the 0.33 and that would be your change for the reactant?
Yes.
Okay.
Yeah, that change column, like you pointed out, that change column is connected to those stoichiometric coefficients as far as what relates from one to the other. Now, since these are the same stoichiometric coefficients, then the change is going to be the same here. And since this is half as much, then this change is going to be half as much. How can I represent that algebraically? I can put a 2x here and a 2x here. And that would make this x. So it's a mathematical way to represent that change.
Okay, that makes sense. Thank you.
Sure, anytime. All right, then we just to cement this home, we mentioned, I think this one last time too. It's another type B problem. Again, we take what's given in the problem to set up our initial conditions. So we just read the problem and calculate our initial molarities, put them in the blocks. If we're not given something, we can assume that it's not present. Then they gave us 1 at equilibrium. Doesn't matter which one, a reactant or product. Once we have that, we can figure out its change and use the stoichiometric coefficients to find the change of the others with that algebraic parameter, or you can do it in association with what you learned in Chem 200, the factor label method, where you convert from one concentration of a reactant or product to another using the molar ratios in the problem. And then we realize which way the reaction has to shift to reach equilibrium, because this is 0. So it has to shift to the right to reach equilibrium. So this has to be a positive here in the change row, negative, negative under the reactants. And so then once we have those concentrations at equilibrium, again, it's a type A equilibrium problem, and we can just plug and chug, making sure that we represent those stoichiometric coefficients in the definition of K using the law of mass action, which says concentration of the products to their stoichiometric coefficients over the concentration of the reactants to their stoichiometric coefficients. All righty. And then we just ended up here. Now this is right before we get to the type C problem. Now the type B equilibrium problem, the ones that we were looking at back here, remember, for this type, they give you some initial conditions and then one at equilibrium and ask you to calculate the equilibrium constant. Type C equilibrium, let me skip through this Q stuff. Type C equilibrium problems are going to ask you to calculate equilibrium concentrations given the equilibrium constant. So type B, you're asked to calculate the equilibrium constant. In type C, you're given the equilibrium constant and asked to calculate equilibrium concentrations. Okay, and we'll get to this in a second, but I just wanted to point out that because it's a big difference. All right, let's go back here. So I'm going to introduce the Q concept now. But before I do that, I want to ask a question. What if you have a situation in an equilibrium problem where they give you a mixture of all the reactants and products? So this isn't 0, this is some value. How am I going to decide where to put the negatives and where to put the positives in my change column? That's a problem. Well, the Q concept can help you figure out where the negatives go in that change row, keep saying column. So let's take a look at this Q concept. Now, the Q is called the reaction quotient. And Q is defined exactly the same as K, except these are usually not equilibrium concentrations. So not equilibrium, not equilibrium. Usually they're not equilibrium, right? If they were equilibrium concentrations, what would Q equal? Anybody?
Okay.
Yeah. Good job. So Q would equal K if they were, and that's a possible Q value. When Q equals K, you know that all those concentrations are equal, but most of the time they're not. So if I have those initial concentrations, that's what these are, initial concentrations that are given to me in a problem. There's a mixture of reactants and products. I can just put them in and I can calculate Q. And then I can compare Q to K if I have K, which I will have in type C equilibrium problems. So I can put them in, I put in those initial conditions, and if I see when I compare it to K, if it equals K, then I know those initial conditions are also equilibrium conditions, and that reaction isn't shifting anywhere, and there's going to be no change in concentration. Now, if I compare Q to K and Q is larger, that means this numerator is larger than it would be in an equilibrium situation. That's the only time I would get a Q equal to K. And if this is larger than it should be compared to equilibrium, then I know that this reaction has to shift to the left to reach equilibrium until Q equals K, and then I reach equilibrium. So when Q is greater than K, the numerator, which contains the products, contains the products, is too great. I need to reduce the amount of products relative to the amount of reactants. And when that reduction takes place, then equilibrium is reestablished. And that's where all reactions are going towards equilibrium. And conversely, when Q is less than K, then the numerator is too small. The reaction should go to the right to reach equilibrium. And so now I can assign, if I can use this analogy here with Q, I can assign the mathematical signs in that change row in the ICE table. Where do I put the positives and where do I put the negatives? So this is a picture of the Q concept. When Q equals K, it's at equilibrium, no shifting, concentrations are constant. When Q is less than K, it's got to shift to the right to make more products. When Q is greater than K, too many products, got to shift to the left. So pictures are nice. I like pictures. Words, sometimes I don't understand. So we'll try to explain things in many ways as possible and attack these concepts from all different angles to try to cement and bring home what's going on. Okay. Any questions so far? We're getting deep into the Q concept. Nothing to do with QAnon. All right, I'm just amusing myself. Sorry about the stupid jokes. But this plate here talks about a reaction that you're going to do in your second lab experiment, experiment 2, when you come in. You're going to set up this reaction here. And here, this is acetic acid. And you're going to be using almost pure acetic acid. So you want to stay away from that stuff. You don't want to breathe it, it'll burn your lungs. The acetic acid and vinegar that you put on your salad is 3%. This is the stuff you're going to use is near 100%. This is ethanol, which you find in alcohol, beer, wine, whatever. Ethyl acetate, fingernail polish remover. It smells kind of nice. And of course, water here. And now they give you 3 different initial conditions. And I want you to tell me which way the reaction is going to shift based off of these initial conditions. And use the Q concept that we just introduced. So there's a few things here that you got to notice, and that is they give you the equilibrium constant. So when you're given the equilibrium constant, you can use this Q concept. If you don't know what the equilibrium constant is, then Q's not going to help you figure out where you are in relationship to the equilibrium and therefore which way the reaction has to shift. So you really have to know the equilibrium constant value. But this first one isn't an application of Q. This is the one that we've been using all along because it has zeros in it. So Can anybody tell me which way the reaction is going to shift for initial conditions for experiment 1?
To the left.
Yeah, it's got to go to the left, right? I mean left, correct?
Yes.
Yeah, because you can't take nothing and make something from it, right? But while we're here, I just want to go back to that thing we were talking about a little while ago. Say instead of 2 for the ethyl acetate, what if they gave you 0 and asked you which way would this reaction shift? It's a trick question. Has anybody got any guts out there who wants to say to the right or to the left? You got a 50-50 chance, punk. That's from an old Clint Eastwood movie.
Would it still be to the left, or is it just no reaction? Because that's just water. That would be
Yes, on the ladder.
okay.
Yeah, it's not the reaction that we want. You can't take water and make wine unless you're Jesus, I guess. And that's what it's saying. If I had 0 here, I can't take water and make something with carbon. Where's the carbon come from? It just doesn't come out of thin air. That's magic or a miracle. So that's why you need some of all the things on one side of the equation or the other before it will react in the reaction that you're thinking of. I mean, maybe this will go into a different reaction. I could see water maybe coming to equilibrium with H2 and O2, but that's a different reaction. We're not talking about that one, right? So anyway, for that first situation, experiment 1, you're absolutely correct. It's got to shift to the left towards the zeros. So we know that we're going to put in the change row, we're going to put positives for that one under the reactants and negatives in the change column under the products because it's shifting to the left. Okay. How about number 2? Which way is that going to shift? And tell me why you think.
Maybe to the right because there's more on the left.
Okay, good. That answer is wrong, but that's an awesome way to learn something. Whenever you have a wrong response, that means you should get excited because now you're about to learn something. And plus, I'll bet you a lot of other people thought that was it too. Well, the answer is the other way. And this is how you get to that conclusion. You form Q. So what's Q equal for that second experiment?
Two times 1,
2 times 1 is 2 over,
3 times 1.
yeah. So this is about, what is it, 0.66, or is it 677? I don't know. It's 2/3. And now Q is 0.667. You compare that to K. Is Q greater than or less than K?
A lot less.
Yeah. So when Q is less than K, that means that the numerator is not big enough relative to K. So it's got to shift. Which way?
Forward to
Yes.
the
Yes.
right.
Correctamundo. Any questions on that one? How about number 3? Which way is that going to shift?
It'll stay the same
Why?
because Q equals K.
Yeah. So it's 2 times 3 over 1 times 1, 6. And that equals K. So when Q equals K, there's no shifting, it's at equilibrium. That is an equilibrium mixture. All right, so you guys are going to have to do that in lab. Now, I just want to mention one more thing that's sort of related, because I think we went through the Q concept and its utility for when you have K and you want to find out what the signs would be in the change row. In this specific example, you see that Q and K, well, you didn't see K, but it is, they're both defined in terms of the concentration of water. And we just learned that any solids or pure liquids are not represented in the definitions of Q and K. So what's going on here? Why is water in here?
Because it's not aqueous.
Yes, it's not. In this example, you didn't know this because you didn't make this up, but this is almost pure acetic acid, pure ethanol, and pure ethyl acetate. So when this reaction does take place, we will see changes in the concentrations of water. It's not in an aqueous solution. It's not the solvent. It's not in the majority. So this is probably the only time you're going to run across this in Chem 201 is in that lab experiment. But you should know that when it's not constant, you can't treat it as a constant. All right, now we get to type C equilibrium problems. All right, remember in type C, they give you the equilibrium constant. Well, actually, a lot of your problems, they're not going to give you this, but you're going to have to look it up in your textbook or online. If they don't give it to you in the words of the problem. Okay, so given 0.5 liter vessel with 0.5 molar H2, 1 mole I2, and Kc, what are the equilibrium concentrations? So in the type C equilibrium problem, what we do now is we employ that algebraic parameter X in the change column, along with our mathematical knowledge for solving equations. So we're going to set up the relationship, and this is why, this is another reason why forming an ICE table with this information will help you form the mathematical equations, which will allow you to relate the equilibrium constant value to the equilibrium concentrations. So hopefully you can appreciate that and use it, because this is only going to get more and more complicated as we look at acid-base reactions, as we look at precipitation reactions, as we look at the formation of complex ions and so forth. So try not to skip this step and think you can do it in your head, because later on it's going to get more complicated. So we want to put our information in the form of an ICE table, and then make our relationships between what we're given, in this case K, and what we want to calculate, in this case the equilibrium concentrations themselves. All right, so I read the problem and I can calculate my initial conditions from the stuff in the problem. They didn't give me any product, so I'm gonna put in 0. Then I can fill out the rest of the ICE table using the algebraic parameter x. I see the stoichiometric coefficients are 1 to 1 to 2. And so I know in the change column, this has to be a minus x. This is going to be a minus x, and this is going to be a positive x. Positive 2x. Now, that's just using the stoichiometric coefficients. I also know this has to be positive under the products and negative under the reactants, because I know this reaction has to shift to the right given these initial conditions. I have a 0. So I do like I did before, and I add up those first 2 rows to give me the equilibrium concentrations in terms of this algebraic parameter x for all of them. And then I can use the definition of K and the law of mass action, which says take these concentrations at equilibrium and put them to their stoichiometric coefficients in this type of ratio here. So I have the concentration of the product to its stoichiometric coefficient here. That's in the definition of the equilibrium constant. And then I divide it by the concentrations of the reactants to their stoichiometric coefficients, which are both 1 here and here. So you have to be careful because the stoichiometric coefficient comes into play in 2 places in the ICE table or in our analysis. It comes into play in this change column here, and also in the exponent when we define it using the law of mass action. Any questions on that? All right, so we're good. So now you just take this problem to your math teacher and tell them to solve it. Or you can use what you learned in math to solve it, which is the quadratic formula. All right, so I assume that you guys all had some experience with the solving quadratic formulas. So again, we have the definition of the equilibrium constant in terms of that algebraic parameter, and I'm given that equilibrium value, or I looked it up in the textbook. So now I multiply all of this out to get an equation that equals 0. And I therefore defined my A term, my B term, and my C term, so I can apply the quadratic equation, which says if I want to find x, which there's going to be 2 roots, mathematical solutions to this problem, there's going to be 2 answers, then I'm going to need to put it in this formula here. And you've seen this before. I'm sure you've done this before. And these days, you don't even have to do it by hand like I did down here. You can just put the A, B, and C in some online app or something, and then it'll give you your solutions, which isn't a bad idea to check your math anyway. So you get 2 solutions for this quadratic equation. And mathematicians will say, yeah, this is great. There's your 2 answers. Physicists and chemists, however, will analyze this and say, this is no good. We're going to throw that one away. This guy is our answer. They say, this one is a non-physical root. It's a non-physical answer. This one is the real answer. So what does that mean? Well, the chemists and the physicists, they just go back to the problem and they show that one is impossible, namely this 2.3. If we go back and we look at this equilibrium, if I have 2 minus 2.3, I'm going to get a negative value. That can't happen. I can't have negative amounts of something. So that one's ridiculous and I can throw it away. The only possible answer is 0.935. Any questions on that?
So this Kc that was calculated is the Kc for like the forward reaction, or
No, it wasn't calculated. It was given
oh
in the
yeah,
problem.
oh yeah, sorry. So okay, so that's for the forward.
Yeah, that's for this reaction as written. So
Okay.
that Kc is for this reaction. Yeah, right there. And type C, that's what makes it different from type B. In type C, you're given the equilibrium constant, or you got to look it up. In type B, you're asked to calculate it.
Thank you.
Sure. All righty. Okay, so now we get to the point where we study Le Chatelier's principle. And this is the principle that helps us, for example, push a reaction to the right or to the left, depending on what we want. The question is, are we always stuck with concentrations that we get at equilibrium? And we studied all this equilibrium concept, but now that we know something about equilibrium, can we use this knowledge to govern over or dictate some possible shifts of reactions that are already at equilibrium? Can we push them maybe towards more products? And Le Chatelier's principle is just that. It's the study of how reactions at equilibrium respond to certain stresses that are put on that equilibrium. So Le Chatelier's principle is really simple. You could read it, and it says something like this. Given a reaction at equilibrium, if someone puts a stress on that equilibrium, and a stress, we're talking about changes the concentrations or changes the pressure or the temperature, then that reaction is going to shift in a way to relieve the stress. So you got a headache, you take an aspirin. If a reaction is at an equilibrium and then somebody puts a stress on it, it's going to react to that stress. All right. So we take a look at this first example. This is a familiar reaction. It's the Born-Haber reaction to form ammonia. And over here, it says, if H2 is injected into the system at equilibrium, it shifts to the right. If pressure is increased, it shifts to the right. If temperature is decreased, it shifts to the right. So these are all stresses that you can put on this equilibrium to make more product. Okay. Now, how do we think in terms of Le Chatelier's principle to rationalize this behavior? Okay. Well, number one, we consider initially a reaction at equilibrium. So this double arrow is valid. All of a sudden, somebody injects H2 gas into that equilibrium. Now it's not at equilibrium anymore. The stress is it has too much H2 gas. Which way does this reaction have to shift to relieve the stress of too much H2 gas?
To the right?
Yeah, I thought I caught everybody sleeping, but obviously some people were not. Very good. Yeah, I'll ask the question again. And you're right, it shifts to the right. Given a reaction at equilibrium, all of a sudden somebody injects some H2 gas. The stress is too much H2 gas. How can it relieve the stress? Shift to the right and consume some of the H2 gas and produce more ammonia. Let's take a look at a picture of that. Oh, and it also goes along with the Q compared to K concept, which way it's going to shift. So Le Chatelier's principle agrees with the Q concept, the reaction quotient. And here's the picture. So here we are at equilibrium. All of a sudden, somebody injects some hydrogen gas into the system. Now we're not at equilibrium anymore. Here, Q equal K. Now, Q is less than K because we have too much reactant. So Q says reaction's got to shift to the right, and so does Le Chatelier's principle. Le Chatelier's principle said, hey, the stress is too much H2, we shift to the right, therefore the amount of H2 goes down. The amount of product, of course, has to go up, and the other reactant goes down a little bit here until equilibrium is reestablished. And Q again equals K. Any comments or questions on that? Okay. And this implies for a lot of Le Chatelier's principle applications dealing with changes of concentrations. So in that example, we suddenly added in some H2, but I can talk about it a different way. And maybe we should take a look at that. Just take a few seconds to look at it. What if instead of adding H2 gas into this equilibrium, I took it out? What would the stress be on the equilibrium?
Shift to the left.
You are correct, but you didn't answer my question. What's the stress on the equilibrium if I took H2 out?
Less reactant.
Yeah, not enough H2, right? So the stress is not enough H2. Le Chatelier says shift to the left, make more. So what I want to do is I wanted to show you guys how simple Le Chatelier's principle is and how you can apply it. All it says is given a reaction at equilibrium, put a stress on it, it shifts to relieve the stress. So if you can identify the stress, you can identify the shift. All right, another situation. Say I have this reaction at equilibrium, and all of a sudden my screen goes completely dark. No, there it is. All of a sudden, let's say I remove N2 gas. What's the stress?
Not enough N2.
Yay. Which way does it shift?
To the left.
To produce more N2. Absolutely. So you can see, you can do this all over the place. What if I take away some NH3 gas? What's the stress?
Not enough NH3?
Yes. So which way does it have to shift to produce more NH3?
To the right.
Yeah. Okay, good. I think you guys are getting it. So Le Chatelier's principle, it's got a big French name, but it's a simple guide to help you figure out which way reactions have to shift when there's some sort of a stress. And we've only looked at changes of concentration so far. The next thing we're going to look at is pressure. But before that, I want to go back to that question of how can we dictate over equilibriums using Le Chatelier's principle. And this is one of the things that have been used, this principle, Le Chatelier's principle, to maximize products in the industrial production of ammonia. So here I have some chamber that injects reactants, and it comes down here and gets heated up, and that causes a reaction in this chamber. Then everything is funneled around to a cooling station that siphons off the product. And what gets recirculated is the reactants. So in this process, you see what they've done is they keep the concentration of the reactants as high as possible, which would make the reaction shift to the right, while at the same time siphoning off the product, which would also make this reaction shift to the right. And that's how they produce ammonia, using the concept of Le Chatelier's principle. All righty, now let's get to the effects of pressure. So this is a moderate pressure. It's not anything great that you'd have to consider things that were not gas, like liquids and solids. So it's moderate changes in pressure, and that's related to volume. So if I decrease the volume, that would increase the pressure, and vice versa. So in this case, we're looking at this example, the smog example again, N2O4 to NO2. Now, an increase of pressure, say I decrease the volume of this container that had these two compounds in it at equilibrium. So I decrease the volume, that increased the pressure. The Chatelier's principle says the stress is too much pressure. How can this shift to relieve too much pressure? Which way is it going to shift? It's going to shift to the left. And by doing that, it takes 2 moles of gas and makes 1 mole of gas. That's going to reduce the pressure, right? Pressure, PV equals nRT. Pressure is directly proportional to N, the number of moles. The more moles you have, the more pressure. So if I shift to the left, I can decrease my number of moles of gas and therefore decrease the pressure.
Could you also say that when you increase the pressure, you're increasing the kinetic energy? So there's more molecules of NO2 like bumping into each other, forming N2O4.
Ah, yeah, that could be part of it. So you have more effective collisions yeah, but it wouldn't increase, I don't think, the force of the collisions. There'd just be more of them, right? Because you're not changing the temperature.
Yeah.
Yes, I agree then.
Okay.
All righty. Any other comments? All right, very good. So and that works the other way around. If I had this reaction at equilibrium and I reduce the pressure, which way is it going to shift? Well, Le Chatelier's principle says not enough pressure, and it's going to shift to the right to increase the pressure. Okay, so it can go either way. Now, the last effect that we want to look at for this chapter is changes of temperature. And I think I'll save that for tomorrow. We'll finish off this. We only have a few more plates. I mean, we're pretty much done. this chapter. And we'll finish it up tomorrow. You're pretty good to do your homework for tomorrow night. You should probably do as many as you can now, and then just leave maybe one or two dealing with Le Chatelier's principle for tomorrow, and bring your questions. And that's it. So I'm gonna wrap this up, and I'll hang out if any of you guys have any questions. We'll take a look at your questions.
Thank you.
Yep, you got it.